Okay, so hello everyone. I'm pleased to present my work about an interferometric approach to spectral wavefront sensing with the first instrument in the big collaboration, which is a Skexeo bench on the Subaru Telescope. So the context of this work and this talk is high contrast imaging for protoplanetary disks and substellar companions. Such as exoplanets. I put some pictures here on the slide of Beta Pictoris and HR 8799 systems, where you can see some exoplanets. In order to do that, there are two goals to achieve. Getting a high contrast, which is typically between 10 to the minus 6 to 10 to the minus 10, to be able to see a companion that is that much fainter compared to the central star, and getting high resolution, which is getting this light at this previous contrast close to the central star, which is typically in the order of tens of milliarc seconds. So to obtain these performances, we need big telescopes, high contrast imaging instruments, and wavefront sensing to correct for the atmospheric turbulences, which is what Skexeo testbed tries to do on the 8-meter Subaru telescope. A quick overlook at the Skexeo. Yeah, the slide is not well displayed. So I put a scheme of Skexeo here on the right. In a nutshell, it's a complex testbed. In a nutshell, it's a high contrast and high resolution bench, which benefits from light corrected with an AO 188. It's divided into two parts, a visible part on the top here of the scheme, and the infrared part at the bottom. Skexeo performs wavefront corrections with an extreme AO system using a pyramid, here in green. And to go further in high contrast imaging performances, other innovative wavefront sensors are under development on the bench, identified in two categories: focal plane wavefront sensors in blue, and interferometric wavefront sensor here, for instance, glint in purple, photonic lantern in orange, and first, which I will focus on during this talk. So all of these systems are well represented in this workshop. You have some names here. So first instrument, which stands for fibered imager for a single telescope, uses pupil masking to make interfere part of a single pupil, here in blue, represented on the scheme on the left. So micro lenses here are placed in the optical path to divide the pupil into subpupils and focus the resulting light beams into single mode optical fibers. These fibers filter the wavefront from speckles remaining from the AO, and their output are placed such a way that the subpupils are remapped and interfere each other with non-redundancy, with the same principle as the Young slit experiment, here indicated with the red arrow. And finally, a prism disperses the resulting interference pattern, which is seen on the camera on the right, where the OPD is a function of wavelength. So from these data taken on first, we fit the fringes with a V2PM method to estimate the complex coherence of each baseline noted ij, which its equation is here on top left. You have several parts. The visibility here, which is equal to 1 for an unresolved star, the amplitude of the two subpupils and the differential piston between these two subpupils. So for now on the scheme on the right, we use this fitting to get these complex coherence terms and to get closure phase estimation from the differential piston from 3 baselines, from which we can get parameters of the target we look at. So it's very with this technique, it's very convenient for science data processing to access the target information. But in the current context of wavefront sensing, we want to keep these differential pistons because on closure phase they are cancelled out. But we want to keep them for wavefront sensing. So here on the top, we use this baseline differential piston and unwrapping for wavefront sensing. So first could be an instrument that make science data at the same time of wavefront sensing. So here I put some features of this instrument. All of that with a lot of spectral channels. So I will make it quick. So for preliminary results, we had OPD measurements on 3 baselines here on the graphs. So the 3 baselines are represented in the 3 colors orange, blue, and green, and the closure phase is at 0 on red for 6 spectral channels. We have a very good consistency with all these spectral channels. But we see significant fluctuations. Here the big peaks at 20 seconds. And the physical causes of this are still under investigations. I remind that it's been only a few weeks that this work has started. So I will conclude here. So SCAXEO is a testbed proposing many wavefront sensor development to get high contrast and resolution in direct imaging astrophysics, adapted specifically to forthcoming ELT-like complex pupils. And with first, we use closure phase measurements for science, and we can use at the same time the differential pistons for wavefront sensing. And so currently lot of efforts are put on algorithms to retrieve absolute OPD between subpupils and understand the big values seen previously on these measurements, and determine how we will benefit from the forthcoming upgrade of FIRST, which is my PhD subject. And so FIRST is seen as a promising instrument that will be able to perform astrophysics measurements at the same time of wavefront control on a photonic chip. Yeah, thank you for your attention.
Great, thank you so much, Kevin. While we wait to see if people have questions on the Slack, I was wondering, you said that the upcoming upgrade of the FIRST instrument is part of your doctoral work. Can you tell us a little bit about what you'll be doing to upgrade it and how that's going to affect your work with interferometric wavefront sensing?
Yes, sure. So here we see a big OPD values that are not that can't be from a wavefront because it's up to 700 nanometers. So we think it's due to the optical path of the different fibers, which had to be polished to have the same length. So with a micrometer precision. So it can come from that, and the upgrade I'm working on. In this upgrade, there is delay lines from which we can control this optical path. And the second thing is to use photonic chip to make the recombination of the several light beams. So it's here at the red arrow. The pupil remapping will be done on photonic chip.
Okay, cool. Very much. Do we have any other questions for Kevin before we move on? We are a couple minutes ahead of schedule, I think. If not, thank you again. It was really interesting.